Hi, this is Philip, and this is going to be a Chapter 30 homework preview. The questions I'm going to go through are number 1, 10, 13, and 17. That's going to be the first video, and then in the second video I'm going to go through 41 and 58. There are a lot of conceptual questions first, from the conceptual questions section in the textbook. And in fact, our primary goal in this chapter is really to understand how induction works, what it does, the kind of situation where it arises, how it really forges the link between what we know about electric charges, electrostatics, and magnetism. There are lots more really complicated calculations we could do, and if we had a longer course we might well do those. But in the current situation, where we only have about a week of the quarter left, we are primarily focused on just understanding the concepts, right? So the homework this time is primarily conceptual, or at least has a lot of conceptual parts to it. So these are the ones I'm going to go through. I just want to say something though about two other problems, namely numbers 22 and 23. Those are about transformers. And they won't make any sense to you unless you read the section in the book, because I haven't made a video on those and I'm not going to. I trust that you can do a little bit of independent reading. It's a short section in the book, 30.7 in the 4th edition. So read that before you tackle number 22 and 23, and they will be very easy, but they won't make sense unless you do that piece of reading first. Alright, let's get started on the actual questions, namely question number 1. Here's the setup for question number 1. We imagine we're driving. This is my car. It is very artistically drawn, as you can tell. We are driving with a certain unknown speed through a magnetic field. The magnetic field we're driving through is the Earth's magnetic field. And we're assuming, the question tells us, that the magnetic field is at right angles to the antenna. Now, if the antenna is straight up, the only place you can really do that is if you're on the equator, say, because if you, this is the Earth. I'm not going to try to draw any map here, but if this is north, like geographical north, geographical south, then you remember the Earth's magnetic field sort of looks something like this. Right. And the only place where, if you stick an antenna straight up, where it's perpendicular to the magnetic field line, is right on the equator, whereas here, in any other places, you're going to get it to be an angle. But that's, not so important. Just a bit of background here. So imagine this is our setup. This is essentially an example of the Hall effect. Remember that what's going to happen is, as this the antenna moves through the magnetic field, it has charges inside. They're going to experience a magnetic force, and the force on the charges is going to be Q, whatever the charge is, times V times B, because the angle is just a right angle, so there's no, no factor of sine or cosine in here. So that means that the charges are going to separate, and we can figure out with the right-hand rule, if I'm going this way, this is my V, B is into the page, so positive charges get pushed upwards. So I'm going to get a plus charges go to here, minus charges go down here. And so this is going to create an electric field inside it, and charges keep moving, making the electric field stronger and stronger until the charge in the middle doesn't feel any more force, because the electric field cancels out the magnetic field, and because the electric field so the electric force is of course Q times the electric field. Electric field inside this conductor that we're going to need to stop any further motion of particles is going to be v times b, right? And if this is not true, then particles will keep moving and making the electric field stronger until it is true. So now I know the electric field inside this this antenna, and then to find the potential difference, well, I know how potential difference relates to electric field. It's going to be the electric field, which is a constant, right? It's not changing with position. Electric field strength times the length of the antenna. Let's say you plug in the values. So I plug this into here. I know what B is. I want a certain potential that's given in the question. The antenna has a certain length that's given in the question. So you can solve for the unknown speed. And that'll solve number 1 for you. So for number 10, I'm just going to refer to the diagram in the book because I couldn't possibly draw it properly. So you've got 2 possible magnets, number 1 and number 2, and we're asking what happens if I move them. Now 2 is actually the easier one. If I move 2, right, then not much is going to happen, because if you imagine the magnetic field lines sort of point out in this sort of brush shape, right? Let me actually draw this on a piece of paper. Right, so this one here, and the North Pole faces down, right? So the magnetic field lines near the bottom are gonna look something like this. And the question is, are they going to cut any flux? Now, what's the flux? What's the surface here? The surface is the surface spanned by this spiral, which you can think of as kind of spirals of staircase surface. It's a bit hard to visualize. You really have to think in 3D here. But it should be obvious that because this is right in the middle, that if this line here starts cutting through some kind of loop here that's part of the solenoid, then this one's going to cut through a loop over here in the other direction, and that overall effect is going to cancel out. Like the flux will not be affected. Right. So in this case, not much happens. The second one is this one here. Now we just have to really think about applying Lenz's law in order to find the direction, right? So if you move this magnet closer, you just sort of draw this a little bit, sort of like this, with the thicker side being the one closer to us. If I have a magnet here, then the field lines, they're going to look sort of like this. Right. Now, what's going to happen is as I move this closer, right, more field lines are going to cut through this surface here, the spiral staircase surface, the outside of which, imagine the wire itself is kind of the railing of a spiral staircase. They're going up this tower, right? And the surface are the steps, that shape. That's what you're cutting through. So one line is going to cut through the same surface multiple times. But as I move this closer, I'm going to increase the flux. So let's just look at one loop. Let's look at the first loop and ask about the flux through this one here. As I'm moving the North Pole closer, right, the flux points to the left, because all the field lines point sort of left-ish. Yes, some of them are going to go out sideways, but the cutting through it is to the left, from right to left. As I move the magnet closer, it gets stronger. The flux gets bigger, right? Because more lines are going to make it through. If you put the magnet right here, you can imagine all those lines are just going to cut through that surface. So if I move the magnet to the left, I'm going to increase the flux to the left. So the change in flux is to the left because it points left and it's getting bigger. Then Lenz's law tells me that the current that goes through this loop here must be such that it creates its own magnetic field created by this current loop. Here it is the solenoid, right? But that magnetic field better point to the right, because Lenz's law states that it opposes the change in flux. And the change in flux we established is to the left because the field is to the left and it's getting stronger. So the change in flux is to the left. So Lenz's law says that the magnetic field, due to the induced current in this, has to point right. So you can think with your right hand curly hand rule, which way do I have to go round this loop here to create a magnetic field that's to the left? I'm going to leave that to you to actually figure out. Of course, when I move this the other way, right, and that's what the question actually is telling us, moving the magnet away, the effect is opposite. I'm moving it away. That means the flux is to the left, but it's getting weaker. So the change in flux is to the right. Lenz's law says the induced current creates a magnetic field that opposes the change in flux. So the induced current creates a magnetic field to the left. So which way is the current going? Is it going essentially up this wire here and round like this, or is it going round the other way and then down the wire? So it's really an application of Lenz's law. This requires some thought. It's a 50-50, right? But you have to think about it. You really have to visualize this loop and visualize your sort of curly hand to go along it. But it's a good exercise to think through this, right? It really sort of trains your spatial thinking, as well as just your understanding of magnetism. So that is number 10. Number 13. So this is the setup for number 13. I imagine I have a rectangular loop of wire, and I'm moving this loop with a certain speed, and the value I got from the book is usually very high. I don't know how you move a wire that fast. There's probably some mechanism here. The wire moves this way. We don't care why, right? We don't care. There's a magnetic field, and the magnetic field here points straight out of the page, because I can tell that little dots, right, means out of the page. So if this wire was just sitting there in a magnetic field or half in a magnetic field, okay, not much of interest is going to happen. But because it is moving, what it means is that the flux inside this wire is changing. Because right now, like the top half, essentially of the loop of the rectangle, has magnetic field going through it, and if it moves up, soon the whole thing is going to have magnetic field going through it. So the flux changes. In a sense, the number of field lines, if you want to think of it that way, in a sort of informal way, that changes. So we want to figure out what is the direction of the current that's induced, and what's the magnitude. We know the final piece of information we're going to need for the magnitude is the resistance of this wire, because of course what we're going to be able to calculate from Faraday's law is the induced EMF, the so-called electromotive force, although it isn't really a force in the technical sense, the potential difference, if you like, that gets created by this motion. Okay, so maybe let's start with Lenz's law. And I'm not going to write this down. I'm going to talk you through it, so you could maybe make your own notes as you're watching this, or even better, you listen to it and then you pause the video and you go through it again yourself, so you make sure you can apply this. The magnetic field points up, out of the page, towards us. As the rectangle moves up, the total flux is going to increase, right? Because a greater part of the area is inside the magnetic field. And so what it implies is that the change in flux, the vector that represents the change in flux, also points in the same direction as the field, namely out of the page towards us. Then by Lenz's law, the current that's going to be induced in this wire, this way or this way, right? The magnetic field created by that current on top of the field that's already there, the magnetic field created by that opposes the change in flux of that field, which means the induced current creates a magnetic field that points down, because the change in flux was up. It points down. So now it's a 50-50. Well, if I go around this way, counterclockwise, then if I think about where my fingers point when they're inside, so to the left of the right wire or to the right of the left wire, sorry, they're going this way, if they're going counterclockwise, right, then they'll always be pointing up, which is wrong. So it means it must be clockwise. Let's check. Yes, indeed, if I go clockwise, then I follow the wire with my thumb. The inside of the rectangle, my fingers, they're always pointing down by the curly hand rule. So I want the current to be clockwise. Well, I know the current will be clockwise. There's actually one more piece of information that the question gives us, which is the width of this rectangle. We call this L, and in my case, in the case of the book, that is 5 centimeters. You might have something different, but it doesn't matter. The method is, of course, always the same. So, what is changing? B is changing? No, B is not changing. The area is changing. The area of the loop isn't, the rectangle isn't changing, but the area that contains magnetic field is changing, and that's the area that counts. So my flux that gets induced is going to be d dt of the, that's right, A area times magnetic field. There's no angle to speak of here because the area vector, right, points straight out the same direction as the magnetic field, so don't have to worry about any cosine factors. It's going to be dA dt times B. The area is only the area that has magnetic field in it, right? That's what counts. How quickly is it changing? Well, if say I call this sort of position x, it would be the length times dx dt, but dx dt is nothing but v. That's the rate of change of area is L times v. Make sure you understand this. Times v. Then you can plug in the values, and you're going to get the potential. Right, this is the. What am I doing? Thank you for stopping my madness. I of course meant the rate of change. That's where the ddt came from. If you are confused, excellent, because it means you're not just blindly following along. I'm blindly copying what I'm doing. All right. So the EMF is the rate of change of flux, technically the absolute value of it, which is this. That comes to this. This of course looks interesting. You're like, L times V times B. Where have I seen that before? Isn't that the same as a wire of length L moving through a magnetic field? And of course it is, because if you look at this wire down here isn't in the magnetic field. This wire up here crosses the magnetic field. This wire here does not. Like this wire here moves in the same direction as V, so you don't actually cut any field lines, right? It just moves along a thin line. This one is the one that cuts the field lines. So really, we've just done the same calculation that we do for a single wire that's right here. Once the back wire enters the field, the story is different, of course, because then those two are going to create opposing potential differences. But opposing EMFs, they're going to cancel out. In fact, we can easily check which way. Velocity up, magnetic field this way. So this one creates a current going this way. But if this one down here creates a current going this way too, well, those can't. They're gonna crash. They're going to oppose each other. They're going to cancel out overall. But while this one here, the bottom wire, is not yet inside the magnetic field, we're going to get this, because only the top wire contributes. Or, in terms of the rate of change of flux, this is going to be true, that the area is equal to this, but only as long as there's still more area to come. Once the whole loop is inside the magnetic field, well, then the flux through it is not going to change, even if it's moving. That is, until you leave the magnetic field, you're going to get a current in the opposite direction. Hope this makes sense to you. So that was number 13. Of course, as always, you have to plug in the numbers. Actually, make sure you understand every piece of this. Let's come to number 17, which is the last one I'm going to do on part 1 of this homework preview. So here is number 17. The idea is this. We have a coil of wire, and again, I sort of try to draw it in 3D, where this side is kind of closer to us and this is a bit further away. There's a coil of wire, which means it's along wire, it's wrapping around kind of in the same spot. So it's not sort of coiling along like a solenoid in a long spiral, but it's all essentially on top of each other. Like something like this. Or I could say the width of this is a lot smaller than the radius, which is the opposite of a solenoid. And I'm given the resistance of this wire, and we're told the number of turns. I'm told the diameter, but we can find the radius quite easily, and the radius is going to be more useful. But of course, the radius might be given in a unit that's not meters, so we'll have to convert. And we're given the magnetic field. The magnetic field points straight through it, perpendicular to the plane of the coil. Right? So if you imagine you put this coil and you span it with a surface, a circular surface in the middle, the magnetic field is at right angles to it. So what's the flux? Well, it's going to be the area times the area of the coil times the magnetic field. There's no angle involved because the sine of 90 is 1, or the cosine of 0, strictly speaking, right? This is my flag sticks out this way. The angle between those is 0. The cosine of 0 is 1. So I don't have to worry about the angle. That's nice. So what's the area of the coil? Well, it's going to be pi r squared. It's a circle, but I've got 20 windings, right? So it's really, again, a sort of very flattened spiral staircase, if you like. Really what I have is I've got 20 circles, except they're sort of hooked onto each other, like you can walk from one circle to the next. So really imagine that I think the spiral staircase is the best. Another example that you might find useful analogy, if you've ever gone north over the border and you've gone to the night market in Richmond, they have these super popular sort of spiral potatoes on a stick, where you get a little stick, like a long skewer, and then they cut a potato into a spiral and sort of roast it, and you've got a spiral staircase potato. Anyway, that's beside the point. The point is the total area is going to be the number of turns times pi r squared, that is my area. The coil is the area per winding. So I multiply this by the number of windings times B. Now, I want to figure out the current through this thing. So for there to be a current, the area must change or the magnetic field must change, and we are told that the magnetic field itself is a function of time, right? I just wrote AT plus BT squared, where little a and little b are just constants. You might be given, in fact you are given numerical values for those. Whereas the area itself stays constant. So the EMF that is induced is the rate of change of magnetic flux, and then We can work this out. This doesn't change, so I'm going to get n pi r squared times dB dt. So I'm going to use the expression I have for b. This is easy to differentiate. I'm going to get n pi r squared times a plus 2bt. So in fact, there's still a t dependence because when I differentiate the second term, of course, when I get 2bt, still depends linearly on t. So the EMF itself is still time dependent. So I've got an expression here. We can evaluate this for the numbers given. Of course, if I want the current, I need to remember to divide by the resistance, which I also know. And then in the second part of this, you're simply asked to evaluate your result for some specific values of time. That should be absolutely trivial, of course. All right. Fairly simple questions, right? And the other ones are also similarly simple. You really just require us to understand the basic principles and then apply Faraday's law to a changing area or a changing magnetic field. But in a way, there aren't that many new concepts here. It's just a sort of rather fun concept with lots of situations to which it can be applied. So in part 2 of this homework preview, I'm going to go to talk about numbers, question numbers 41 and 58. I will see you there.